Okay, so let's get to the second half of today's lecture. We start with approximate dynamic programming. We'll talk about approximation in value space and then a special type of approximation in value space, parametric cost approximation. Just to bring you back to where we were, we have a discrete time dynamic system. X is the state, U is the control, W is the disturbance. We optimize over feedback policies, which are control functions that satisfy the control constraint. And given an initial state and given a policy, there is a cost associated with that, which is given by this expression. It's the sum of the cost per stage over n time periods. And we take the expected value of that, and the optimal cost function is the optimal over pi. We minimize over pi, not over all controls. And the dynamic programming algorithm computes the optimal cost of the tail problem that starts at state xk and goes from k to n. And it's given by this expression here. It goes backwards, starting from the terminal state, and then given the optimal cost of the tail subproblem at time k plus 1, it computes the one at time k using this computation. And at the end, we find the optimal cost and also the optimal policy by putting together all the minimum, all the controls that attain the minimum in that expression. And okay, so what are the practical difficulties? The first one is called the curse of dimensionality. There are just too many tail subproblems to solve, too many values of xk that are relevant. If you have a continuous state problem, there's an infinite number of tail subproblems. Okay, so you can get an idea of the difficulty. We are going to need to do discretization in a continuous state problem. And okay, suppose that you have a problem with continuous state with, let's say, n state variables, and we choose 100 discretization points per axis. So the number of states is going to be 100 to the n. There's an exponential explosion with of the computation with the dimensions of the state and the control spaces. If the problem is natural discrete or combinatorial, like the scheduling problem that I have discussed, we have a quick explosion of the number of states as the search space is, as I have mentioned earlier. There's an issue also with the length of the horizon. If it's a very long horizon, then you have to do proportionally as many computations. And what if the horizon is infinite, okay? Now, that actually calls for a somewhat different methodology that addresses explicitly the infinite character of the horizon, although a long horizon, an infinite horizon problem can be approximated by a long horizon problem where length is sufficiently high. Okay, so that's one curse, the curse of dimensionality. There's another curse that people don't mention, and that's the curse of modeling. We need to know exactly the system equation, and we need to know the statistics of the disturbance, the probability distribution. And it's often very hard to construct such an accurate mathematical model of the problem. However, in many problems of interest, a simulator of the system may be available, may be easier to construct than a model. And we can use a computer model. And it turns out that this overcomes the curse of modeling, and this is part and parcel of the overall methodology of approximate dynamic programming.
How can you simulate the model if you don't know the conditional distribution of xk plus 1?
Okay. A system equation and the probability distributions will be embedded in the computer model. In other words, the computer will be able to simulate the probability distribution, but it doesn't have a paper expression. Okay? It's embedded in the software. There are many engineering problems where you can, for example, let's take a communication network involving nodes, queues, and very complicated protocols for moving around messages. Now, it is impossible to write equations for all this stuff. On the other hand, you can write a computer program fairly easily. That's the kind of situation I'm talking about. Okay, here's a third curse. And this is the following. The problem data may not be known well in advance. Instead, a family of problems may be of interest, and the data of a problem, of the particular problem that you are interested for that day, may be given with little advance notice. Like take, for example, a truck that's supposed to go around the city and perform various services at service points. Now, the map of the city may be available, and however, the location of the service points may not be available until early in the morning when the driver starts out to go around. So what does that mean? It means that I have the data of the problem, but I have very little time to solve it. Problems have to be solved with little notice, and that's a difficulty. Moreover, you may start with a given problem, and the problem data may change as the system is controlled. Like, for example, the truck driver that goes around to serve the service points, there may be some new service points that may pop up at different places as he's driving. So he has to do online replanning, on the go, quite fast. And that creates time constraints which can exacerbate the situation. So these are the three main difficulties that we're faced with. And let's talk about one approach for addressing them, which is approximation in value space in conjunction with limited look ahead. Okay, let's first talk about one-step look ahead and then approximation. The idea is to simplify the dynamic programming computation, and here we just replace the optimal cost function, the object of dynamic programming, by some kind of approximation, which I'm going to be referring to as J tilde. So instead of JK, we use some J tilde K. That's easier perhaps to obtain. And we use in the dynamic programming minimization, in the dynamic programming computation, instead of JK plus 1, we use some J tilde K plus 1, which is easier to compute in some way. Okay? Of course, there's a lot to discuss here. How do we find J tilde and so on, but that's what's coming. Okay, now this is one step look ahead. We can also look ahead several stages, and at state xk, we can solve a two-step dynamic programming, a three-step dynamic programming, or an L-step dynamic programming that starts at xk and uses as terminal cost J tilde k plus L instead of the optimal jk plus L. Okay? Now, in the one-step look ahead, you use at time k the control that attains the minimum here. In L-step look ahead, you solve this L-step problem. You obtain a control for the first stage, and then a control function for the remaining stages, and you apply the first control. So I look ahead 10 steps. I find a 10-step policy. I use only the first component of that policy, and then go to the next stage. Then I roll my horizon, and I go another 10 steps forward, solve that problem, use the first component of the solution, and keep going forward. Other names that are used for this are rolling horizon control or receding horizon control. They are really special types of multi-step or L-step look-ahead policies. So that's the idea. It's very, very simple. However, implementing it is not so simple, and there are many, many different ways of doing it. Okay, so let's focus on the one-step look-ahead computation at stage k. This is it here. A key issue is how do we choose the approximate cost functions, the J tildes that we need in this computation. And another issue is how do we deal with the minimization and the computation of the expected value. This seems trivial by comparison, but it is not. The minimization may be a complicated minimization. The expected value may involve knowing the probability distribution of the disturbances. Taking that expected value is still a substantial computation, let alone if you don't know the probability distribution, you have to use simulation. Okay, so there are a number of approximation approaches for computing J tilde k. One is parametric cost to go approximation. We use as J tilde some function from a parametric class that depends on some parameter vector Rk, or a weight vector. We call them weight vectors, and the weights of a neural network, if you want to think of them in those terms. So we have a whole class of functions that are parameterized by this vector here, and we choose a parameter, the parameter Rk that achieves some good effect. The parameter is tuned according to some scheme. Typically, the idea is to bring this J tilde k close to the exact Jk. Okay? So that's parametric cost to go approximation. I'm going to say a few things in the remainder of this talk. Another possibility is rollout. Rollout is an algorithm that uses some suboptimal policy, some known, easy to compute, heuristic perhaps policy, and we can suppose we can calculate the cost function of that suboptimal policy. Then we use as J tilde k in here the cost function of that heuristic. Now, this cost function can be calculated either by simulation or analytically, and let's talk about that tomorrow. The third possibility is, instead of finding the optimal cost of the tail subproblem in this computation, replace the tail subproblem with a simpler problem, just simplify it. This is called problem approximation. I compute exactly the optimal policy up to some steps, and then instead of using the optimal cost of the real problem, I approximate that with something simpler. That's another approach. Again, we're going to discuss this with examples tomorrow. Okay, so now here's a schematic that summarizes the approximation in value space approach. We are at state xk. Let's see, let me try to use this. We are at state xk, and we do a dynamic programming minimization that involves just L steps, and the future is summarized in this approximate cost function. So we have a look-ahead minimization over L steps. There's a minimization involved here. There's also an expected value because the disturbances are in here. And then there's a cost to go approximation. So there are these two pieces, look-ahead minimization, which is exact up to L steps, and approximation at the end. Now, let me summarize some of the cost approximation possibilities within this picture. Okay, so we have this, we are at state xk, and we want to calculate a control, and we formulate this L-step look-ahead problem. This is the minimization, and then the first question is, how do you approximate this jk with some j tilde? And here are some of the options. One possibility is to use just a simple choice, like take j tilde to be 0, okay? Then we just say that the future doesn't matter beyond L steps, and that's my approximation. Of course, it goes, with this approach, you have to have a sufficient number of steps so that you get a reasonably good approximation. But it's it's a legitimate way of doing things, although I'm not going to discuss it very much. The other possibility is parametric approximation, where this is chosen from some parametric class. Rollout, which I mentioned what it is a little earlier, and tail problem approximation is still another approach. So there are these two issues, L-step look ahead and the future, and the approaches for the future are what you see here. And now let's look at approximations in the minimization, in the look-ahead minimization. There are two things that can give us trouble here. One is the minimization over L-step policies, and the other is the expected value. We can do approximations in both of them. We can replace the expected value with some deterministic value. Just use nominal values for the WK, maybe their expected values. This is a long, this is an approach with a long history. It's called certainty equivalent control. It's motivated by certainty equivalence in linear quadratic problems, where if you replace the uncertain quantities by their expected values, you still maintain optimality. So, but you can use the same idea in a broader context, and it has worked well over the years for a number of different contexts, although, like always in approximate dynamic programming, there are no guarantees of good performance. Okay, you just try it, you simulate it, maybe it works, maybe it doesn't. Okay, now about the expected value. One possibility is to compute it by simulation, but perhaps you may cut corners in the simulation. You may do limited simulation. Besides, the simulation here must be done for every possible value of UK, and you may do some controls and simulate their effects at corresponding cost, but after a few simulation samples, some of these controls are obviously bad, appear to be obviously bad, and then you sort of discard them from consideration. That would be a case where you use approximate simulation. And there's a technique called Monte Carlo tree search, which theoretically can find the exact minimum and uses confidence intervals, statistical confidence intervals, to discard controls that statistically appear to be bad relative to other controls. Okay. So here you see the entire landscape of approximation in value space, and each one of these little things, little approaches, has a theory behind it and applications. So now let's say a few things about a simple choice of J tilde. One possibility, like I said, is to use a cost to go approximation, this is 0, discard the future, or to use the terminal cost function if the problem has a terminal cost function. In some problems, there's a goal state. The objective is to get close to a certain reference point, and after n steps, but if we use limited look ahead, we may replace the goal state objective with a penalty. Introduce a penalty for not reaching the goal or not getting close to the goal. So with a simple choice of J tilde, generally we expect to use long look ahead. However, this involves a lot of dynamic programming computation, because still dynamic programming problems, even with a moderate number of stages, can be difficult to solve. And often this means that we have to do things offline, perhaps using parallel computation and so on. The alternative is to use a short look ahead, but use a sophisticated choice of J tilde. So we try to get close to what we want for the future and then use limited look ahead. And the idea now it is important that J tilde is a good approximation of the optimal cost to go produced by the exact dynamic programming. And here's where a lot of the action is. Many different ways to compute J tilde, and we're going to describe some of those. Some of them are offline, some of them are online, and they involve some theory and some sophisticated implementation. Okay, so this is the picture that we're trying to complete, and we're focusing on one of those approaches. We're going to focus on one of those approaches for computing J tilde, which is parametric approximation. So that's what we want to compute. And here we start with an approximation architecture, a class of functions parameterized by a parameter vector, a vector of weights that we can tune, we can change, and correspondingly change j tilde so as to make it close as we want to the optimal cost function. And then we use j tilde in place of jk in one-step or multi-step look-ahead schemes. And this is called an approximation architecture. And the role of the parameter vector is to change the shape of the approximation so that it's close to the optimum. And there are two key issues. First, the choice of the parametric class. What do we use? Do we use a linear architecture, a nonlinear architecture, neural network, radial basis functions? Which one of those do we use? And the second is, how do we train the architecture, which is the method for tuning or adjusting the weights. So choose an architecture and then have a good method for training it. And major class of architecture is the so-called feature-based architectures. Okay, so given a state xk, it has some obvious characteristics, okay? And some of these characteristics, you can view them as, we call them features. So given a state, we may extract a vector of features. These f1k up to fmk are scalars. There are m features that depend on the current state. And this is the feature vector. This form of feature vector associated with xk. And the feature-based approximation architecture introduces a dependence on the state through its feature vector. In other words, states that have mapping to the same features, they are approximated by in the same way. And this j hat k is some function, perhaps linear or nonlinear in Rk. Now, the idea with feature-based architectures is that a good cost-to-go approximator perhaps has to be complicated, nonlinear. But if you manage to squeeze into these features a lot of the nonlinearity, then you can use a simple j hat. You can just linearly weight, for example, the features, because a lot of the nonlinearity is captured by these features. Well-chosen feature vector, a good approximation, is often provided by linearly weighting the features. Okay? So we have these features, m features associated with the state xk, and we weigh them with scalar weights. Okay, it's the linear combination of the features, and that's the approximation. And I'm showing here also as an inner product. And notice that, so here is the diagram for this architecture. The state is mapped into a feature vector. We extract these features, and then we weigh them linearly, and this linear combination of the features is the cost approximation at state xk. Now, notice that there is a mathematician's view of what this involves. It involves subspace approximation. We can view these features as basis functions that span a certain subspace, and we are looking to approximate the optimal cost-to-go function, this jk, with some j tilde that is some vector in this subspace. Perhaps some projection will do, or something similar. All of these ideas are in play here. So subspace approximation idea with a choice, a proper choice of basis functions that control. And you can have, of course, nonlinear feature-based architectures, but linear architectures are also very common. So what do we choose as basis functions, as features? This is a major issue in approximate dynamic programming, as indeed in all kinds of machine learning. How do you represent a certain function of interest? What kind of features do you use? Any generic basis functions, such as polynomials, wavelets, radial basis functions, and so on, can serve as features that can be linearly weighted. However, in some cases, problem-specific features that can be handcrafted, that sort of are based on our understanding of the problem. And one example where it's a major success story of artificial intelligence is computer chess. You can view a chess position as a state which has some characteristics that chess players can recognize. Like, for example, the material balance, the mobility of the pieces, safety issues about the king, strategic features of whether there are open files that one player has over the other. All of these are characteristics of the position. And in chess programs, these features are weighted, typically linearly, with weights chosen by experience for the most part, to give a score of the position. And that's the way chess programs work. They look ahead a certain amount of time, and then they evaluate the resulting positions by extracting the features, linearly weigh them, and select the move that gives the best approximate score based on this approximator. So here the state is the position, the board position, the control is the choice of move, and like I said, most chess programs use a linear architecture, and the choice of weights in computer chess traditionally have been manual. In other words, these weights are hand-tuned, and based on the results of that the program achieves, the programmer tweaks the weights so as to correct whatever is perceived as a deficiency of the program. There are some computer programs that choose the weights by some kind of systematic procedure, a machine learning procedure based on least squares fit, using a training set obtained through grandmaster play. So in this kind of training was used with the Deep Blue chess program that beat Garry Kasparov, the world champion then. They collected a lot of positions and the choices of grandmasters, and they tried to choose the weights automatically so that the program scored the position more or less like the grandmasters do. Okay. So that's as an example of a handcrafted type of architecture. Okay, so suppose we have an architecture, an approximation architecture. How do we use it in dynamic programming? Well, a common way is to do the following, at least for finite horizon problems. We start with j tilde equals to the terminal cost function, and we sequentially train approximation architectures backwards. So given a cost to go approximation j tilde of k plus 1, we use one step look ahead to construct a large number of state cost pairs. Okay, so this is the state, and this expression here is the result of the dynamic programming computation using the approximation architecture at the next step. Now we have a set of training pairs, states and corresponding dynamic programming results, and we put them together into some kind of a least squares program. And we minimize over the parameters of the k-stage architecture of this expression. In other words, we try to fit j tilde k to these values here, and we may add a regularization term. Okay, this is common in regression problems, where r bar is some initial guess and gamma is a positive regularization parameter. Now, this is a problem that has special structure. It is an additive sum of many components. The number of training pairs here can be tremendous, very, very large. So this involves a sum with many, many terms. And if you try to use traditional gradient-based techniques, then you have great difficulty because at each iteration you have to make a pass through the entire training set, and that's a lot of computation. Instead, typically people use incremental gradient methods, which have seen a great deal of use and popularity in the last few years. It's what's called backpropagation methods. Incremental gradient methods, backpropagation methods, stochastic gradient methods are all more or less synonyms for the same thing. In incremental gradient methods, you calculate a little gradient of a single component, and you move the parameters from the current value along that component gradient, and you have to process only one component, only one part of only a single piece of data from the training set, rather than the entire training set. You break down a gradient calculation into many little gradient calculations, and each one of those you can do by using a gradient computation that's called backpropagation.
What is the relation between Q and M? M is the number of features.
Q and M.
Q is the number of
the number of training pairs.
Training pairs.
Yes, we select
the number of, if I remember correct, the number of eyes.
The number of features. Yes. Yeah. This. Okay. So here we have an arbitrary approximation architecture, not necessarily feature-based, but certainly feature-based architecture is an important special case. And we just calculate, let's say, 10,000 pairs like that, put them through a regression, then go to one step backwards, collect training pairs, do a regression, and so on. Now, here's an important thing. If the architecture is linear, like a linear feature-based architecture, this is a linear least squares program. Linear least squares problem, because this is a linear function of the weights, so this is a linear least squares problem. It's much easier. It can be solved analytically in principle, although in practice, people solve it often by incremental gradient methods, with an iterative method. If the architecture is nonlinear, as it is in neural network problems, I'm going to come to that in the next slide, then this computation is more difficult, but still people have been having a lot of success, although sometimes it amazes me that there's so much success with them, because in my mind, this is a challenging regression problem if J tilde is nonlinear. It seems to be working well for many types of problems. I can't argue with success.
Can I ask a question? In the previous slide, why R does not depend on you? Are you approximating jk plus 1 evaluated at f of k, or jk plus 1 evaluated at xk plus 1?
No, jk plus 1. No, jk plus 1 is a function of two things. The next state, this fk, that's the xk plus 1, and the parameter that we know already from the previous regression. Okay? So if you look at this expression, the first term depends on u, and the second term depends also on u, and the expected value also depends on u. So we minimize over u.
So the question is whether rk can depend on you, can give better results.
No, it cannot depend. It does not depend on you. It depends on the training set only, and the training set does not involve you. Okay. No. Okay. Okay. So let's talk about neural networks as an introduction. You can use neural networks in this sequential training scheme. Starting from the end, compute a weight vector for a given stage, and then go back one stage and solve a regression problem and compute the next set of weights and so on. So we train the state neural network, compute j tilde k using a training set generated with a stage k plus 1 neural network, which defines j tilde of k plus 1. And what is a neural network? Well, a neural network, you can view it as an approximation architecture that looks like linear, but it involves two parameters. It involves a parameter vector r that weighs linearly something that looks like features, but the features themselves depend on a parameter vector v. So in this approximation architecture, there are two parameter vectors with different roles. V can be viewed as a vector that defines features for the problem, and R can be viewed as the vector weights that weighs these features. So we view this as a feature vector, we view R as a vector of linear weighting parameters, and we optimize simultaneously. So we simultaneously the features and the weights weighing on those features. And that's a big thing. Okay, perhaps it's a price to pay for it, but it's a big thing. It relieves us from the requirement to select features. The neural network does it for us, okay? And that's a major convenience. On the negative side, we have a nonlinear architecture, a non-linear least squares problem, and all sorts of potential computational difficulties, including local minima of the regression objective, and including, if you look at a computer, 3D graphs of neural network cost functions, you see that are just horrendous, okay? How in the world gradient methods can work with these functions always mystifies me, but it seems that they work, and I can argue with success, like I said earlier. Okay, so that's the bottom line. By training the V set of parameters jointly with R, we obtain automatically generated features. And that brings me to the end of my lecture. Tomorrow, I'm going to start right from this point and discuss what is the structure here, the multiple stages, and an idea about how the gradient computation is done, and so on. And then after we're done with parametric approximation, we're going to get into other value, other approximation in value space methods, and finish the settlement. I'm sorry, I'm rushing, and I know that I've exceeded my time, and I apologize for that, but I never know how long it's going to take me. And I've been delighted to hear your questions. So keep asking questions, but I'm trying to do the best to keep within my time limit, even though I'm not I may not be fully successful.
Questions? Just make sure to use the microphone. Maybe all the questions were online.
This n is another parameter actually. This n over there in the sum in the number of features is another parameter. Because you want to approximate j tilde by some j hat, you actually do two-stage approximation. This is a two-stage, in my understanding, optimization program. I mean, so you want to, and then you want to do some kind of, there are many regularization steps that we need to take to approximate this. Is this my understanding correct?
Yes. M is also an architectural choice. How many of those you use. And in fact, there's a lot of complexity that's been, in this simple form, it hides in a lot of complexity with the multiple stages, nonlinear layers concatenated with, interleaved rather, with linear layers and so on. R, the vector R, corresponds to the last linear stage, and the output of the neural network up to the last linear stage is this phi, and V, rushing ahead to tomorrow's lecture, V is the collection of all the weights up to the very last stage. Okay, that's how I would view it. And of course, M depends on how many layers there are, how many units per layer, and so on. Yes.
Can you please discuss the relationship between approximate dynamic programming and the reinforcement learning? Is it the same thing? Is it similar things?
It's just that people with different backgrounds, different names. because my background is in dynamic programming, I use the term approximate dynamic programming, which I believe, I may submit to you, that is more descriptive. Now, reinforcement learning, what do you reinforce? I'm not sure. So to some people, this has meaning. To me, it has less of a meaning. But there are entirely, and there are other names, by the way. There's neurodynamic programming, okay? And there's a grouping control theory, which is very active, which they use the term adaptive dynamic programming, which regrettably has the acronym ADP, just like approximate dynamic programming. But they call it adaptive dynamic programming, and they mean more or less the same playing field, okay?
Can you go back to the slide where you initiated the approximation of the dynamic program?
You mean this slide?
Yeah. So is the algorithm also sensitive to knowledge of the conditional distribution of W given X and U? How sensitive is it? I mean, is there a massive respect to? Because at this point there, right, you need to take expectations. So you need to know the distribution of W given X and U. So does it cover that if you have incorrect model to be sensitive?
You're absolutely right. This computation involves knowing the probability distribution of WK so that you can compute analytically the expectation. However, there's a version of this backwards training technique that can use a simulator. Okay? This is the Q-learning technique that we're going to discuss tomorrow. So one of the first things we're going to discuss tomorrow is a version of this algorithm, this training technique, that uses a simulator for instead of an expectation.
Another question I have is, so this method to work, you need to have, you put the word here, grandmaster to train. You take the example with the glue, the big glue. The big glue was successful because they used the grandmaster to train.
Yes.
Right? So what if you don't have a grandmaster to train?
Well, I have dynamic programming, right? And it's a pretty good grandmaster because it's mathematically based. It's better than a grandmaster. But I'm a little facetious here. What we use is the dynamic programming formula. I agree with you, it's not the same as the training, it's just a different approach. It's called an expert training approach, where if you have a grandmaster, or if you have a good policy, any good policy, okay, you can use it to create a training set, and then what you're going to get is a cost function approximation that will try to emulate that good policy, or emulate the grandmaster play. This is closer actually to, in some ways, it is close to the technique of approximation in policy space that we're going to discuss tomorrow.
It's almost like saying, I just need to have a point. The grandmaster training is equivalent to finding out, use it because that corresponds to the optimal policies. It's almost like when you use that knowledge, you create something which is based on the optimal policy.
Well, grandmasters don't always play optimally, okay? So they are suboptimal. Their play is suboptimal, but close to optimal. And within the grand scheme of his things here, it's acceptable as an approximation technique. It beat the world champion, remember? So there must be something good about it. No, I think with that match, the world champion was beaten, and since that time, the gap between machines and humans has actually been increasing, regrettably.
So maybe there's another question.
Yeah.
Can I just go back to terminology about reinforcement learning, approximate learning, programming, and obviously others? Is there any way to get the community to use the same terminology? Because obviously we do compute students all the time. I brought two classes here to listen to you. I talked in the class about reinforcement learning, the same thing as you're talking and you will be talking tomorrow. And I'm sure they will be confused.
I think that there's a gap that's hard to bridge. I think that, first of all, control people have a limited understanding of artificial intelligence, and the other way around. So some terms have more meaning for one group than for another. So I know of efforts, systematic efforts and quite passionate efforts on the part of some people to bring people from different groups to use, if not the similar terminology, use similar notation. But it just hasn't happened, and I don't think it will happen based on my experience. It was a bit of a shame. I personally find that artificial intelligence and control theory have important and complementary contributions within this field. It's a happy union of ideas between computer science and control optimization, but I don't think that it will take another generation, perhaps, before people agree on terms, and perhaps even concepts. So you're hearing a biased view here.